warahmatullahi wabarakatuh, dan salam sejahtera. Alhamdulillah, bersyukur kita kepada Allah Subhanahu Wa Taala dengan limpah dan kurnianya dapat kita berkumpul lagi pada petang ini di seminar mingguan INSPEM. Dan alhamdulillah hari ini kita bertuah kerana dapat bersama kita Profesor Dr. Muhammad Yunus bin Abdul Shukor. Beliau merupakan profesor di Fakulti Biotechnology dan Biomolecular, dan sedikit latar belakang beliau. Profesor Muhammad Yunus bin Abdul Shukor merupakan anak kelahiran Perak. Beliau sekarang bertugas di Jabatan Biokimia, Fakulti Bioteknologi dan Sains Molekul UPM sejak tahun 2002. Bidang kepakaran beliau adalah biokimia alam sekitar. Beliau mendapat sarjana muda Bioteknologi dari Imperial College of London pada 1993 dan kemudian mendapat ijazah PhD di UPM pada 2001. Beliau juga telah melakukan ekspedisi ilmiah ke Antartika pada 2002-2003 dengan kerjasama ASM dan Institut Antartika Argentina. Aktif dalam penulisan dan menghasilkan banyak makalah terujuk. Mengikut carian saya sebanyak 120 lebih lah atas kerja yang beliau telah hasilkan. Pada 2017 beliau juga telah dianugerahkan sebagai Top Research Scientist Malaysia TRSM bagi tahun 2017. Tanpa melengah masa, saya jemput Profesor Dr. Muhammad Yunus untuk membentangkan kertas kerja beliau. Dengan segala hormat, silakan.
Pertama sekali, thank you Dr. Rahizat. Thank you INSPEM for inviting me. I have to use the English language because some of my students from Nigeria are attending the talk. And first and foremost, I'm a biochemist, not a mathematician, but I have a brother who is very going into the mathematical world. And before I start, I have to acknowledge that this work actually comes from him, and my contribution is minimal, but I really do understand part of his work. So if you look at the title, a new discovery of mathematical formulation for sums of power, of which the Faulhaber sums of power for integer force are its umbrella, which without further ado, I'm going to start. But first, pardon my grammar because I'm a bit rusty. So as an introduction, sums of power has gathered interest in mathematicians since ancient time. If you look at Pythagoras and his simple formulation, you can see that 1 plus 2 plus 3 up to n. So imagine you add 1 plus 2 is equal to 3, plus 3, 6, and going on. Now, about 1,000 years ago, or 2,000 years ago, they probably have limited amount of papers. So that if you write up to 1 million, it will be very tiresome. It probably takes you 3 or 4 days to complete. Fortunately, Pythagoras has designed a formula equation, a short form. So if you want to sum up to 1 million, for instance, we just replace the n with 1 million, 1 million plus 1, and divide by 2. That is the summation up to 1 million. And then Archimedes followed by being able to sum up until the power of 2 using the following equation. And this is followed up by the Indian mathematician Aryabhata, and his sum of power, cube power formulation, which means he's able to do it up to the power of cube, power of 3. And this is followed by the Egyptian Abu Ali Hassan al-Haytham, up to the power of 4. And from here, as we know, during the Dark Ages, after the Dark Ages, it was this mathematical formula and its theory was taken by the Western world, by Thomas Harriot. And then it spurs an improvement in terms of the power, up to which power you can sum up. And Faulhaber, a very eminent mathematician, has managed to do it up to the 17th power. However, Mohd, which is a Turing Award laureate, which is like a Nobel Prize for computer science, noted that in his book, Faulhaber actually managed to formulate up to the 23rd power instead of the 17th power. And then the following formulation sums power is by Blaise Pascal. And in 1913, Jacob Bernoulli, he managed to do what everyone before this didn't manage to do, which is to be able to produce a formula which you can sum up any number of power of n. Instead of 1 power 3, you can 1 power 201 plus 2 to the power of 201, okay, and so on and so forth. But remember, all of these started with 1. So you have to start 1 power of 3 plus 2 power of 3. And then comes William Chen from the Center for Numerical Bioinformatics from China. He managed to do it in odd powers, which means if you look at the x, you can start x with any number. For instance, 5 plus 6 plus 7 power or something. So 7 plus 1 becomes 8. And if you look at the power series, it's 2m minus 1, which means the value becomes odd. If you see 2 is times 2, 4 minus 1, it becomes 3. Now it's the power becomes 3, 5, 7, and so on and so forth. So this is odd power. Unfortunately, for even power, it's not there yet, if I'm not mistaken. And then adopting Yoshinari Inaba symmetry, another great mathematician. Gauthier from the Royal Military College of Canada, Dr. Napoleon, he managed to do it using arithmetic terms of progression. And then his result for m is equal to is given as follows. Okay, the problem is that the search for simple formulation for some power, it has attracted many mathematicians, and it's not an easy subject. And a lot of proof has been given, a lot of publication, but then what we want as a scientist or a mathematician is to have a simple equation so that you don't have to say, what if 1 to the power of 2 million plus 2 to the power of 2 million or 3 to the power of 3 million? And you need to have a simple formulation so that you don't tax the computer. Nowadays, people using computer. Still, if you imagine how to find the Clay's mathematical price for finding the biggest prime number, up to now is 20 million. They use the formula we call machines. You plug it into the machine prime number, but still the computer takes a long time to calculate. And now the largest prime number is 20 million. Still, you can try your supercomputer to find bigger terms of that. Okay. So the purpose of this work is to construct a simple equation. The thing about mathematician is that if you look at my Scopus profile, I have about 172 publications, about 2,000 to nearly 3,000 citations, and my index is 27. But if you look at Andrew Wiles, the most famous mathematician in the world because he solved the Fermat-Last theorem, he got a 2016 Nobel Prize, which is being given by the Swedish country, Sweden, which is equivalent to Nobel Prize in mathematics. If you look at his Scopus profile, he has only 11 documents, citations about less than 1,000, but his index is lower than me. That's a problem. That is not a problem with mathematician. People, there are non-mathematicians who is attending this talk. You have to understand that mathematicians, there are very few mathematicians who can do stuff. But we life scientists, there are 2 million life scientists. So we can get up to maybe 2 million citations in theory. But mathematician number theory, you probably have about 200 to 1,000. So maximum you can get is 1,000 throughout your work. Okay, so you cannot equate the Scopus or Google Scholar from mathematician to the life science. You have to appreciate mathematician. You can see that they get Nobel Prize even though it's index of 9. That's how different is mathematician. So it started in 1993. I was at Imperial College. I went into this Imperial College student shop, which you can get anything, and it's books and so on. I picked up a New Scientist magazine, and I read one article. It mentioned that Andrew Wiles of Princeton University, he has announced a 1,000-page proof of eventually what it translates is the Fermat-Last theorem. Pierre de Fermat was a mathematician. He produced many conjectures, but one of his last conjectures worth several million pounds or several million USD is to prove the following equation: x power n plus y power n is equal to z power n. As you imagine, x power of 0, n equal to power 0, it's fast. So because 1 plus 1 cannot equal to 2, right? So if n the power of 1, then this equation is correct. So 2 to the power of 1 plus 3 to the power of 1 is equal to 5 to the power of 1. And our famous, what we have explored is the n power of 2. We use this n power of 2 a lot in our equation, finding the diagonal line, because 3 power of 2 for diagonal lines is equal to 4 power of 2 is equal to 5 power of 2. Okay, so you know that the length of the diagonal by squaring the summation of the square of the angles, the length of the sides. So what Fermat asserts that there is no integer solutions for n bigger than 3, other than trivial solution, which I mentioned earlier. So what this means is that a mathematician has tried to prove that, okay, n power, I think they use computer, by brute force they managed to do n power 100, the equation is not true for n power 140,000 something digit. But as a mathematician, we are not satisfied, because you can prove up to, you can prove up to 140,000, but you cannot prove until 1 million. For instance, whether this equation x power 1 million plus y power 1 million is equal to z power 1 million, whether there are numbers which you can satisfy the equation. That is where Fermat comes in. Eventually, Andrew was took over, because his ambition from the very young age is to prove Fermat-Last theorem. So when I read that article, I tried to prove it myself. Of course, this is a futile effort. I'm not good at mathematics. So I gave it to my brother, Mr. Shukor. He was 18 years old after SPM. So he took that particular work, starting from SPM. And when he graduated from Yunus, he was offered a scholarship to Oxford by UPN in aerospace. But while he was at Oxford, he spent too much time on mathematics that he know his PhD. Okay. But without further ado, I have to introduce him, because he is the one who find this new theorem. Okay.
Okay, it's me, Shukor.
Okay.
The early attempt to prove Fermat-Last theorem by dissecting equation x power n plus y power n to z power n into the most basic form of x plus y and y minus x, or in its symmetric forms. Indirectly, we developed the sum of power symmetric function, and the complete form was found in the year of 2001 as follows, where the summation of S1I is a symmetric function. First 5 equations from the generalized equation, when we expand it, you can get power 1, power 2, power 3, power power 1, power 2, power 3, power 4, power 5. Okay. Derivation, there's a several derivation method for this formula. One of it is data analysis method. What you do is that you tabulate the value for various n, and then you okay. Okay, you tabulate these equations and then enter. Okay. Okay. And you form in a metric form, solving the coefficient, and you get the you solving the coefficient, you got the alpha, the coefficient for the symmetric function. And yes, for the odd and even p. Another one is algebraic manipulation method. For p equal to 2 and n equal to 2. Calculating this form, you get x plus 2, x power 2, x1 power 2 plus x2 power 2 equal to x1 plus x2 power 2 divided by 2 plus s power 2 over 2. Consider p equal to 2 and n equal to 3. You get this form, and then finally you got this form. In the same procedure for term from 2 to n, by considering a general formulation for this form, x1 power 2 equal to a multiplied by our symmetric function power 2 plus b multiplied by s power 2. You can get calculating for sum n and tabulating the data in the table, and curve can be constructed from the data. You get this curve, and combine of the result, you get the generalized equation for power 2. arithmetic progression, which is equal to symmetric function power 2 divided by n plus n multiplied by n squared minus 1 divided by 12 multiplied by s squared. S is basically is a difference between consecutive arithmetic terms. Repeating the same procedure, you get for power 3, power 4, power 5, and so on. But the beauty of this equation, you can see the repetition of the coefficient here. And the power is from 3 minus 2, you got 1. From 4 minus 2, you got 2. This is a descending power 2 for all the equations. Here for power 6, you can see you can basically use the same coefficient here. Okay, the another method is using matrimonial theorem and product arithmetic terms in generating sum of power for arbitrary arithmetic terms. The multinomial theorem states that if P is non-negative integers, then x1 plus x2 plus up to xk power P equal to summation of binomial expansion P R0 R2 Rk multiplied by x1 R1 x2 R1 till xk Rk. In this research, it is proposed that the multinomial theorem for arbitrary arithmetic progression can be expressed as the power of arithmetic sum descending by 2 for each subsequent terms of P minus 2j. The equation is given as follows. Every monomial term can also be expressed in the same form, like this one, where k is equal to p minus 1 over 2 for odd power, p divided by 2 for even p. More information regarding how to construct this equation can be read from the paper here. The multimodal also can be expressed as follows. This term. The proposed conjecture reiterates that for all monomials, for all arithmetic progression can always be expanded as follows. For odd P, like this formulation. For even P, like this one. For even P, like this one. For odd P, for this one. And for general term for odd P, here like this one. And even P here. And collecting the coefficients, we get a summation of x power p equal to 1 minus alpha naught plus beta naught plus gamma naught multiplied by symmetric function powered by p. And so on. And for even p, we get the same pattern. Combine the above result, which is identical to the proposed sum of power generalized equations. From the formulating the generalized equation for sum of power. The coefficient theta m involved in the generalized equation can be simplified as follows. Theta naught is 1, theta 1 is p multiplied by p minus 1 over 24 times m squared minus 1, and so on, up to theta 6. In binomial expansion form, we can simplify as this form. Evaluating the data here, we get the main idea how the coefficients related to each other. Consequently, you get theta m equal to 1 over 2 the power 2m multiplied by 1 over 2m plus 1, binomial expansion for p 2m multiplied by pm. And you get this expression. Or you can use a software to simplify this equation. You can get this term. Theta m is actually 2 times p over 2m. Binomial expansion of p, 2m, and minus 1 over 2, summation of jm with the limits n minus 1 over 2. Or applying Bernoulli identity, you get this expression. Okay, these are proof for the sum of power of general formulation and the derivation of sum power through binomial expansion of elementary arithmetic term. Basically, the idea is that to express the arithmetic term as a symmetric functions. Here we got the symmetric symmetric mean value minus n minus 1 multiplied by s divided by 2 is this basically is the first term, the second term, and then the last one is n term for even n, and for the odd n you get this expression by considering binomial expansion of x plus y power of p, which is given as follow, and substituting x equal to x symmetric function x divided by n and y equal to n minus q s over 2 into the equation above, where q is an odd number, use the even n. Like this equation. The summation goes down. Simplifying, we got this term. For odd, we get this term. Simplifying both equation yields this form. Let's find the equation is for even p, we combine all the result. For even p, for odd p, another form for even p, like this one. For odd p, when we both the equation, we got the generalized equation, which is identical. Where same, this u is for p minus 1 over 2 for odd, is for divided by 2 for even. For our equation, setting the first term and then the difference between the consecutive term to 1, this equation reduced to the classical Faulhaber sum of power for integers. The power sum of integer generalized equation is given as follow: x power p, summation of I power p up to limit n equal to summation of theta m multiplied by a symmetric function p minus powered by p minus 2j over n powered by p minus 2j plus 1. Since I, the summation of arithmetic progression is given as follow, then we get the expression before Faulhaber. Consider when p equal to 2. We substitute the value here. We get 1 over 6 multiplied by 2 power n power 3 plus 3 power by n multiplied by n 3n power 2 plus n. Or we can use the generalized equation for power 2. Just insert the arithmetic terms n, I, we get the same value. Fermat-Last theorem. Setting n equal to the generalized equation reduced into the Fermat-Last theorem. Because there's two terms, Euler used to use the parameter from finding proof of p equal to 3, where 2u equals to x plus y, which is basically symmetric function. And some the mathematicians tried the same symmetric function for power 5 and 7. Riemann zeta function. Expanding the general equation for non-integers or non-negative power yields another term for Riemann zeta function. When you expand the powers goes to infinity. Simplifying, you got this term. For integers, you use the integer sum and t equal to 1. Then you get this expression. Then Riemann zeta function is equal to 1 over n power s, or n summation n power negative s. You get this expression, and theta naught is basically is this form. Theta 2, theta 3, theta 4. Since Riemann zeta function is n approaching infinity, taking the limits for all the terms to the infinity, you get the simplified form for the Riemann zeta function, like this one. Okay, rewriting the equation, you got a simplified form, like this one. Okay.
To summarize, sorry for the audio, a bit slow. To increase the audio a bit. The general equation for some power entered this paper, you can extend to on many other uses because it is simple and elegant formulation, which we prove by numerical simulation. The new formula includes Faulhaber sums of power, and most other formula derived for sum of power expression in form of the most basic elementary symmetric function of the arithmetic progression. Since integer is part of the arithmetic progression, it offers some new form of power, some form of power, as an alternative as a competitor to Faulhaber formulation. You can also generalize the equation to extend to real numbers powers, which are useful for extending the sum power to Riemann zeta function and numerical summation for rational as well as irrational 1/3, 1/, or something like that, power, irrational numbers. When n is, you set n is equal to 2, as we mentioned earlier, you reduce it to Fermat-Last theorem, and you can express Fermat-Last theorem in a polynomial form of symmetric function. Those are the avenues which you can explore further. And my brother first think of this idea, and he put his whole work in Math is Fun forum, where a lot of mathematicians throughout the world use their pseudonym. You do not know their identity. And if you can see that here are the new formulas by my brother, which is the pseudonym is Stanger ZV. Stanger ZV, a new math formula, with achieved nearly 34,000 views, whereas the new twin prime number, which is a new formulation, which is not covered by this presentation, it received 200,000 views. If you look at down below, at number 3, say Po Shen Lo, which is a Chinese mathematician, discovers a new way to solve quadratic equations. Within a few replies by the eminent mathematician in Math is Fun forum, they just shoot it down and say this is not new. It has been done before by, okay. So if you put your stuff in Math is Fun forum or any math forum, people will shoot down your work very, very fast. And since 2012 up to now, there is no one refuting the work being produced there. Another thing is that since we talk to many mathematicians, some of them dismiss the idea straightforward because they think these are not mathematicians. So they say that we don't want to see your work, even though we email them, they don't reply. But some of them, if you look here, we receive a reply from Prof. John Coates. Prof. John Coates is the Sedlarian Professor of Pure Mathematics, University of Cambridge. Apparently, he's the doctoral supervisor of Sir Andrew Wiles, who proved the Fermat-Last theorem in 1995 and got an Nobel Prize for it. And in 1978, as part of his PhD work, Andrew Wiles published with John Coates on PADL functions and elliptic units, which is a portion of the work being carried out here. If you look at the email, first, he applauded that we have tested the method numerically, which means it's always an excellent test of accuracy. Then he said it is possible that you have found something new. Okay, but then he also mentioned that there are a lot of big p-adic literature, being a p-adic expert himself. So related to Bernoulli numbers, and if you look at the last sentence, which lies, also Riemann zeta function, which lies at the heart of a lot of current research in arithmetic geometry on Iwasawa theory, which is part of the Andrew Wiles proof of the Fermat-Last theorem. And he said that he had a quick look. He said it could be something new. This is where I believe the strength of the work, because coming from John Coates, is actually the head of mathematics department in Cambridge. And he mentioned that you have to explore on your own. This was sent roughly 2011. And we did publish this work in Journal of Discrete Mathematical Science after getting a lot of rejections from quartile 1 journals. And I can show proof that this quartile 1 journals rejected for mundane reasons, something like we don't have the time to evaluate your paper, or your the slot for publication is already full. These are like, I think we're not sure why if they reject it based on the content, they will probably reject it outright. So we managed to find a small journal which published this work, and you can read all the experts here. You can read the work there, and I think this work can be is being explored by my brother into producing several new works like the new twin prime numbers, and because he's not doing mathematics, he's doing mathematician as a hobby. So he's limited by time. But then again, most mathematicians in the early ancient world are what we call it hobbyists, mathematicians. They're not like pure mathematicians which goes to university. But then most of them actually, nowadays you have to get approved from eminent person from universities to look at the formula and to evaluate whether it's right or it is wrong. If it's right, maybe 5 years time, this mathematical formula should be in the Malaysian mathematics textbook. It's a new formula by Malaysian, or it could be, I'm not sure. I mean, it could be very, very famous one day, but we have to see, look and see. It's been like 11 years, 12 years from now on. So the last slide are the references cited. You can go through the reference. I thank you, INSPEM. I thank you, the organizer, for inviting us to this exciting INSPEM. And I also apologize for any shortcomings coming from us. Okay, thank you.
Okay, terima kasih Prof Yunus di atas perkongsian ini. Mungkin ada soalan ataupun pertanyaan daripada para peserta. We open for Q&A. Is it any question for others?
Assalamualaikum. Rizal sini. Assalamualaikum.
Waalaikumsalam. Teruskan.
Okey. Saya nak tanya yang pembuktian series yang banyak-banyak tu, guna induction ke bagaimana? Ataupun ada induction, the proof by induction tu ada ke? That one you ada?
Tak, dia tak prove by induction, dia prove by terms tu. Kita sum in all the terms and simplify it, and it's identical to generalized formulation.
Tak, maksud saya di sini ada banyak summation. Daripada mula tadi pun ada banyak summation awak buat. So
the summation is up to n to from 1 to n to n. It's like induction basically, but it's in a way like we collect all the terms and simplify it.
Okay, let me just put it sekali lagi. Masa mula-mula slide tu awak ada slide Pythagoras lah, mula-mula tu. Kan?
Tahu.
Okay, yang tu, all this actually is if you venture into this direction, all these are proven by induction.
Ya, kalau macam okay.
So kalau maknanya kalau you go down the road of these fellas summing benda-benda ni, is part of the game. Actually there are 3 ways to prove. Maybe saya agak aja. Maybe dalam awak punya penulisan tu, reviewer mencari 3 benda. Pertama, proof by induction, or direct proof, or proof by contradiction. They were searching for that first. And since they could not find that in the writing, ini selalunya memang kalau mathematician ni tak jumpa 3 benda tu, then people start to macam okay lah. You get the point lah. So these are the
point, because kalau macam terms very very simple one, you can use term of induction. Another one you can prove. Basically, you should look at the manuscript with 68 pages. I just condense it very short term. Basically, the reason why I couldn't publish before because I couldn't find the proof for it. So you should work for all n. Basically, what I did is like to express the thermodynamic terms in a form of symmetric function in the form of n. So when we prove it, we prove for all n, basically. The summation from this side, left-hand side, equal to right-hand side of all n.
Okay, so the proof strategy was using proof by induction ke direct proof?
Direct, by direct.
Direct proof.
Yeah.
Okay, so kalau summation, if it involves summation and some series or some sequences, direct proofs takes time
I have done it. I've done it because it is a new method. Basically, you express each term in the symmetric function. That's how you can do it. If you want to try to do reduction for the generalized equation, it takes time because it is very complicated one. Basically, it's lots of or perhaps someone can continue to work.
Yeah, you can help him.
Because I have no time to prove find another proof.
This is where we need the help of eminent mathematician, like you.
No, I'm not an eminent mathematician. Putus, sorry. So the idea is that you prove it directly lah, and then publish dekat journal in 2011, the one that you showed.
That we publish it at the journal. That's why, because it's been proven. You have to read the paper. That's why it's been accepted.
It's 49 pages long.
It's like 68 pages long paper.
Which journal?
You can see. I give you the link.
The last slide.
Last slide.
Sorry about
And
that. To scroll very fast. Yep.
Yeah, this one.
Mathematics ni.
You can go through it.
So this article in this journal is 40 pages long.
68 pages, if you're not mistaken. There's lots of other theorem inside it, but I couldn't put in the presentation. It'd be a lengthy one.
Okay, all right, thank you.
So, ada lagi soalan ataupun komen? Berapa lama kajian ini telah dilakukan?
Dari umur 18, sekarang umur 46. 20.
Almost 30 years, nearly 30 years.
Nearly 30 years.
So, agak lama.
That's why I don't want to consume more in the Fermat theorem. When I found that Andrew Weiss found it, that's why I stopped it. Because I don't want to spend another 10 years doing it.
Okay, ada lagi soalan? Okay, dalam ruangan chat ada. What is the daily use of sum of power?
Sum of power, you can extend it to Riemann zeta function, and then you can do encryption, finding the pattern for prime numbers for encryption.
As we know, encryption is in our everyday life. Our pin codes rely upon the sum of prime numbers, large prime numbers. Since the prime numbers, nobody can find a formula of it. Once you use quantum computers, they probably can hack it. But up to now, all this information, sum of powers, prime will eventually goes to Riemann zeta function. Eventually, you will face with prime numbers, and it's very important in cryptography work, which is saving our bank account and so on.
Okay, terima kasih. Mungkin ada lagi persoalan daripada para peserta. Ya, agak lama kajian ini, selama hampir 30 tahun.
Ya.
Mungkin ada kajian lanjutan atau?
Ada, kita ada unpublished paper untuk alternative sum of power. Itu masih preprint, saya tak dapat lagi proof dia. Sebab malas nak buat yang panjang. Itu pun ada big formulation.
You can go to Math is Fun forum where my brother under the pseudonym Stranger ZV, or you can Google Math is Fun and Theory of Symmetric Function. There are several formulas being put forward there. You can go there and look at all the comments by the mathematicians in that particular forum. And also, I wish if any mathematicians from UNSPEM or from elsewhere wishes to collaborate, please contact us. We are happy to help and publish together.
Okay, ada soalan dari ruangan chat. Why the author not proceed with PhD?
Kadang-kadang kita malas sekarang, yang kita dah berumur malas. Benda ni hobi, just hobby. Bila saya boring, saya buat mathematics. That's it. Itu je.
I mean, in English is that he wish to pursue PhD, maybe in UPM or INSPEM for that particular matter, but like mathematics you can do at home. Everyone is doing what mathematicians are doing nowadays offline, and you produce great results, and that's it. I think he likes it as a hobby, but if you have any offer, probably he can take it later on.
Yeah, insyaAllah. Okay. Okay, sekiranya tak ada lagi persoalan, sekali lagi saya ucapkan terima kasih kepada Prof. Dr. Mohd Yunus dan Muhammad Shukri atas pembentangan dan perkongsian ini. InsyaAllah di lain hari kita akan jemput lagi sekiranya ada kelapangan dan
maybe new theories. We publish new theories. We can come back to INSPEM weekly seminars.
Okay.
So thank you so much from INSPEM. I think you're probably a bit hesitant to invite me as a biochemist but then I think it is a great start. We'll probably have to invite other non-mathematicians to bring something new to the seminar. It's very refreshing. I applaud INSPEM for having these weekly seminars, and I wish you all of the best.
Okay. Terima kasih Prof.
Sama-sama.
Dan terima kasih juga kepada peserta yang yang mengikuti program kita pada petang ini. InsyaAllah kita akan bertemu di minggu hadapan insyaAllah dengan perkongsian ataupun perbincangan daripada pembentang lain insyaAllah. Saya sudahi dengan wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh. Terima kasih semua.
Salam.
Waalaikumsalam. Masya Allah.
Waalaikumsalam. Thank you so much.